Awesome. Thank you. Thank you, everyone. It's a pleasure to be here. So yes, my talk will be about how we do self-supervised learning for 3D vision and applications like autonomous driving, but also robotics in general. So just TRI, we're the Toyota Research Institute. Our mission is to develop automated driving. And as I mentioned, not just that, but also robotics and other human amplification technologies. It's not just about automation, but it's about also the human in the loop. We do a lot of cutting edge research published at various venues like CVPR with a large practical impact because we have many transfer opportunities. So as I mentioned, whether for cars or robots, we do things around scene understanding, self-supervised learning, which I'll talk about today, simulation auto-labeling, behavior modeling, learning for planning and control. So an example of a scientific challenge we are working on is depth estimation. For those of you that are not familiar with it, it consists in taking a single RGB image or multiple RGB images, feeding it through a depth network and predicting the depth, which is the per pixel range, how far objects are in the world. Now, a natural question in the autonomous driving world, where LiDAR is available very frequently, is a question: why would you care about monocular depth at all for driving and robotics? And the first answer is because camera is the most common sensor, as you all know. The other interesting point is that even if you have LiDAR or multiple different cameras, typically for self-driving applications, they are arranged, for instance, around the car. And so they might have a very wide baseline, which breaks typical stereo methods. And the other good reason in multi-camera or multi-sensor rigs is redundancy. As we know from the Byzantine generals problem, you need multiple ways to arrive to the same solution, for instance, to be robust, including as the previous speaker was talking about. And finally, from a research standpoint, if you're looking at 3D detection from images today, monocular depth is the current major bottleneck, and why it's so far behind LiDAR 3D detection, for instance. So a key research question that really animates us is, can we get robust 3D vision thanks to large-scale self-supervision? And here's an example of what we're able to achieve. And in particular, what you see here is on the upper left is an image fed into a network that produces the depth map on the lower left. And we can actually reconstruct the metrically scaled point cloud, so points in 3D points in meters. And that's because we're using projective geometry as a source of self-supervision to predict the dense depth of a scene from a single image. Note that for those of you that are familiar with self-supervised learning, this is very different than your typical ImageNet self-supervised learning, because here we're not just pre-training for a task, like not just representation learning, but we're actually self-supervising the target task itself, meaning after self-supervised learning, the network produces the target output that you want, in this case, the depth. So we've done a couple of different papers on that, and one that we're particularly proud of is called 3D packing for self-supervised monocular depth estimation, which we covered last year in a CVPR or oral paper. And we presented the network. It's called PackNet that you see here, this little encoder-decoder network, which is learned via the view synthesis approach of Zhu et al., which is called SFM Learner. So in the SFM, structure for motion setup, so only from raw monocular videos. And basically, it's summarized in this diagram that you see on the left and the reprojection equation. For those of you that have taken basic camera, the pinhole camera model in your computer vision classes, you should recognize this equation. And our key contribution here in this paper was in replacing pooling and upsampling operators, which are typically done in the encoder and decoder, respectively, of those networks, and replacing them by learning compression and decompression modules that we call packing and unpacking in order to preserve details that are important for reconstruction. Because here you really care about reducing the amount of photometric ambiguities, which means reducing the areas of your loss that are not giving you clear supervision for your model. And one way is to preserve details as much as possible. And one of the things that was interesting with this work was that it was the first, to our surprise, self-supervised method that was outperforming supervised learning on this task. And we've since then improved it. You can find code and data online for this. We're also organizing a workshop and a depth estimation challenge using our dataset called DDAD, Dense Depth for Autonomous Driving, which is happening at CVPR on the 25th of June, so this Friday, the last day of the conference. So as I mentioned, we've been extending that work in multiple different directions, actually, literally. One paper that we just recently put on arXiv is called FSM, for full surround monodepth. And the idea is the following. Most of the monocular depth or the depth estimation networks you're seeing, even 3D detection, is focusing on just the front camera, a single camera, single image, just looking in the front. But obviously, for driving, you need full situational awareness, so you need the full 360-degree understanding of the world. And as I mentioned before, why is it hard? Well, it's hard because you don't have like too many sensors. There's some redundancy, but you minimize it for cost reasons, obviously. And so what typically ends up happening, like in our cars, for instance, you have 6 cameras and they have really a minimal overlap. And this is really quite common in practice. So this is why we've been studying this problem and proposed this paper, full surround monodepth from multiple cameras. So here, for instance, is an example of 6 cameras taken at the same time, so time synchronized. This is actually from the new scenes data set. As I mentioned, this configuration is quite common in self-driving. And what we're able to produce, so what you see here in blue, the little blue dots that you might have a hard time seeing, represents the LiDAR points that are in the overlap between cameras. So they really represent the overlap between cameras, which is very minimal. And obviously here you have a very wide baseline, clearly not frontal parallel, generalized stereo problem, which is really difficult. And yet we're able to obtain with a single network the 360 point cloud that you see on the right. And the key insight to get there was when you're doing self-supervised learning for a monocular depth estimation, as I mentioned, you do the view synthesis approach, which is you're reconstructing a past frame from the present frame by predicting the depth and the ego motion, and then using this rigid warping to basically reconstruct the past frame from the current frame pixels. Here, we're generalizing this idea to spatiotemporal view synthesis, where we're leveraging a general spatiotemporal context. So what it means is that in typical stereo, you have 2 frontal parallel images. You reconstruct the left from the right, or vice versa. And they need to overlap a lot, which is a small baseline. But here, they're not overlapping enough. So you can't really recreate, let's say, an image from the second camera from the first camera, because they overlap too little. And so instead, you can reconstruct the image, let's say, from the second camera using the first camera at a different time. And so really, we're generalizing these spatiotemporal relations and leveraging that to learn a single network for all the cameras by reconstructing from different time instances and different cameras. We're adding a couple of different details, which I encourage you to check the paper. One is multi-camera pose constraints, and one which is actually very surprising in its simplicity and effectiveness is just masking, which to make basically to ignore some parts of the loss, which are wrong. And we know, for instance, because of some self-occlusions, which is also common in robotics when you have a mobile manipulator that's hiding part of your field of view. There's many results in the paper. I encourage you to have a look at it. We're also looking at the ablations of these different components. That's about it for FSM. How well does it work? So here, what you can see is 6 cameras from our theorized DDAT dataset. And you see the 6 cameras, the 6 depth maps produced, and then the point cloud, the 360 3D point cloud. And again, because here we're knowing the extrinsics, so the relation between cameras and calibration, we have some notion of metric scale. So actually our point cloud is metrically scaled. So meaning we feed the 6 images into a single network and it produces 360 point cloud in meters. And that's consistent across cameras, even though they have very little overlap. All right. So one thing that's pretty neat in all I've shown you so far is that we can rely on prior knowledge from geometry to self-supervise because we know the reprojection equations. But that's actually, and we assume that this reprojection equation is correct because that way, if we make a mistake in the view synthesis, it's not because geometry is wrong, it's because the depth network weights are wrong, and backpropagation will adjust these weights to make it agree with geometry. But the problem is that geometry might be wrong because everything is a model, right? And so the pinhole camera model actually doesn't work really well on certain weird or unknown camera geometries. Maybe you don't know the camera parameters, or maybe the camera is something like you see here, a catadioptric camera, a high field of view like fisheye camera. It might be, like not super rectified like pinhole camera. So you have like some distortions maybe on the sides. Another common application in driving is you have a dash cam, which sits behind a windshield, and the windshield acts as a very weird lens. Imagine this, you can make it even more complex with rain on the windshield, or even like crazy applications like underwater robotics, where water acts as a very weird changing lens. And so the cool thing about that is that you can actually make this approach of view synthesis work, self-supervised learning work, again, supervising by predicting ego motion and reprojection, where you are also learning the reprojection. And that was like inspired by work by Adrien Gaidon and co-authors, where they were predicting the Pintle camera model parameters. But actually, you can just take a general camera model inspired by Grossberg and Nayar and just full-on predict the per pixel projection operator. And this is what we've done in this work called neural ray surfaces that we presented as a NORAD 3V last year. Code is also available online and pre-trained models, and you can try it out. A couple of Redditors have had fun using it with like crazy cameras, like action cameras for like biking and stuff like that. So you can have fun. So, okay, that's great. All that is self-supervised learning. You can extend it from multiple cameras, even when they have weird geometry. But in practice, you're never always just without any label at all. You always have some form of supervision. And we've been studying like just scaling up these approaches and like how do we go beyond self-supervised learning in a sense. And so some approaches, like obviously that's very well known, is semi-supervised learning, where you have some of your data that is labeled, maybe let's say with an active learning loop, or maybe part of the environment, you have like a 4-beam LiDAR and you get some 3D points in the environment very sparsely. Another one is auto-labeling via differentiable rendering, where here the geometry you're using is a bit more complex. It's the geometry, the physics of light, and you're using those predicting parameters and re-rendering. And then the last one is sim to real, where you're using supervised learning, but in simulation. And what you have to do in an unsupervised way is overcome the sim to real gap. And through our research, we found that there's a general insight connecting these different approaches, and namely that self-supervised learning is what enables you to make the most of what little supervision you have. So this is why self-supervised learning is not just scientifically interesting for us, but also practically relevant. So I'm going to go a little bit more into details about how self-supervised learning is actually key for the scalability of those 3 types of approaches: semi-supervised, auto-labeling, and sim to real. So for semi-supervised learning, there's a traditional training setup, and we had a paper at Coral where we're looking at like combining some 3D supervision for some points. Let's say if you have a 4-beam LiDAR, which is common for automotive, with just cameras. And that's great. You train still a monocular network. But one thing that's interesting is what if you also have partial point clouds available for inference sometimes? After all, if you assume you have a 4-beam LiDAR and you're training data, why don't you use it if you have it, at test time, at inference time? And so here, that's one of the work we're presenting at CVPR this year, which is called Sparse Auxiliary Network for Unified Monocular Depth Prediction and Completion. And here we show that the same model, again, the same network weights, can be used to leverage partial point clouds, both at training time and at inference time, whether they're always present or only sometimes. And that's something we call dialable perception, where you can turn on and off the LiDAR sensor, for instance, and the model is always able to predict what you want, which is the depth of the scene. And the way it works is you have the standard decoder depth network like PACnet or Monodepth 2. But in addition, we have sometimes a sparse point cloud as input. And we're using sparse convolutions and learning a representation that we are then learning to inject into the skip connections of the encoder-decoder depth network. And these adapter weights to do this injection in the skip connections are able to learn to inject it when we have it, and then otherwise you just use the skip connections as normal. So these are some example results, and what you're going to see here is sometimes you're going to see some kind of color-coded height map flare up with some sparse points like right now, and this corresponds to when we turn on a sparse LiDAR and off. And this is literally like when we add an input to the network or turn it off. And if you can see, the network is still able to predict when it's off, and when it's on, it's able to predict quite accurately, matching the actual point clouds in the world that are sensed directly. In the case of auto-labeling, which is the second of the self-supervised plus approaches that I mentioned, once again, self-supervised learning is key for what's called analysis by synthesis, or also the approach called inverse graphics in general. And so in a nutshell, The idea of our recent CVPR and ECCV papers that are described here, they consist in feeding an image to a deep network that then outputs, like some scene level parameters that can then be used as an input to a renderer. And that renderer can then take those scene descriptions and then re-render the input image that was fed into the network. And that way you have reconstructed the image. And if you are correct, again, assuming you have no bug in your renderer, then it's because your network that's deconstructed the image into the scene parameters was wrong. Then that works. And if the renderer is actually differentiable, you can backpropagate through, again, that photometric error, this pixel comparison, to optimize the weight of the network that is deconstructing the image. And so here is an example of the network in action. And again, these scene parameters, they correspond to object placements, they correspond to object shapes in 3D. And here you're seeing the optimization loop through the differentiable renderer of the cars and their shapes and the translation, rotation, and everything. This work, the CVPR oral that I presented last year, used LiDAR to add not just a 2D rendering loss, but also a 3D, more structured rendering loss using LiDAR and partial matching of the point clouds. But in our follow-up ECCV work, we had extended this to rely only on monocular depth and replacing basically the LiDAR by pre-trained detectors at training time to really go like full vision. Beyond depth estimation and object detection, our research also covers other tasks that are crucial for autonomous driving and robotics, including learning them together and a multitask learning framework, which is very common for computational reasons, because you're constrained, so you have to plug multiple networks, like combine multiple networks together. And so an example is our work on panoptic segmentation, which combines instance and semantic segmentation in a unified model. And last year, we presented at CVPR a novel method that was both 4 times faster and slightly more accurate than the state of the art. And this year, we are presenting a new panoptic model that learns pixel level embeddings to simultaneously represent instances and categories, both of objects and regions. So which means that you get every pixel can have like a latent vector, a vector, and the average of those vectors inside an instance represents the instance well, but it's also pretty close to other instances of the same category and far from other instances of other categories. And that's for objects, but we can also represent ground or building or sky with those embeddings too. More details in our paper that we're presenting this week at CVPR called Hierarchical Lovash Embeddings for Proposal-Free Panoptic Segmentation. One problem with that so far is I actually, if you haven't noticed, I drifted into supervised learning land, which is where does these labels come from? Because obviously semantics are defined by humans, so they cannot be purely self-supervised. Right, my face could be called a schmerg. We just collectively decide as human beings to call this thing a face. So here, this is basically this little parenthesis, detour through supervised learning is to bring me to SIM. Because instead of manual labeling, which we don't think scales, we're thinking a promising avenue to get scalable semantic supervision is simulation. But of course, there's no free lunch, so it comes at a cost, which is the domain gap that might hurt generalization performance. So overcoming this gap is called solving the sim to real transfer problem, which is a specific instance of what's more generally called unsupervised domain adaptation. And so very recently also, we put on arXiv a paper called Geometric Unsupervised Domain Adaptation for Semantic Segmentation, GUDA for short. And it works by multitask mixed batch training. So it combines synthetic supervision with real-world geometric self-supervision, the photometric loss that I talked about before, to learn a domain invariant network that predicts both semantics and depth. So as input, sim and real world. As outputs, you're getting semantics and depth. And you can only pay a supervised loss on semantics when you have sim samples. But on the real world, you can pay the self-supervised loss, which you also can pay in sim. And so we're basically having this combined multitask objective with mixed batch training to learn these joint features that work across the domain gap. And we show that combining semantic objectives in sim. So again, it's semantic. You're saying this is a face, this is a shirt, etc. With geometric ones that say warp this, reconstruct this image, because geometry tells me if you're right about your depth estimate. This is how geometry tells you how it should look like, the reconstructed image. So by combining these two, we can reduce the domain gap. And then performance, what we found in this paper is that we find that performance, this is the graph you see on the upper right, performance improves linearly so far up to like 42,000 samples that we've been using with both synthetic data quality and quantity. And so one of the things that's interesting is that we've been using state-of-the-art synthetic data from a company called Parallel Domain to try to really push the limits of see how far we are from just replacing supervision for semantics by synthetic supervision. And I think in our experiments, we saw that roughly 6 or 10 times more synthetic data should be able to cover the gap if the trend follows. And of course, the trend is going to plateau at some point, but so far it's just linearly showing that it's improving. So to conclude, I've talked to you about first the self-supervised part, like purely self-supervised, where we are using geometry as supervision on videos, and again, direct supervision to solve the task. And then I talked about, like, in a more practical setting, you care about using whatever you have at your disposal. Like self-driving and robots is just so hard that you cannot ignore things you have at your disposal, even though they might be tricky to combine together. And so that's why there's some interesting research problems there to do scalable supervised learning or self-supervised plus. And what I've shown you is that actually self-supervised learning is the key to really unlock this like advantage of the extra little things you have. In the case of semi-supervision, semi-supervision can be essentially phrased as self-supervised plus sparsely supervised. Auto-labeling of the differentiable rendering, it's basically you're injecting prior knowledge about objects and you're combining it with a differentiable renderer. In the scene-to-real transfer case, it's literally synthetically supervised plus real-world self-supervised. It's a bit like Neo learning Kung Fu with Morpheus inside the simulation and then fighting it out and becoming better in the real world, where we know it's actually the Matrix. So it's another simulation. So that analogy doesn't really work very well. But anyway, there is a really nice saying from Alyosha Ifros, which is the AI revolution will not be supervised. And I definitely believe in that. And also known as driving is more fun than CAPTCHA. So you don't want to be clicking on pixels as human beings for the rest of our lives just to supervise machines. So yeah, we do a lot more work. This is just a slide with a lot of the research we do, and a big thank you to a lot of the collaborators. It takes a village to work on autonomous driving. And here's our presence at CVPR. Lots of people in my team, myself included, would be here. We released a lot of code and data. And yeah, just feel free to reach out and come to our workshop on Friday. Thank you.